Today I want to, this is my topic. I teach physics for the first year, second year, all years of undergraduate. And one of the things that I like to do in my classroom is to use computer programming quite heavily to learn any kind of physics, whether it's mechanics or um, wave motion or thermal physics, of course. All right, so this is something that I like to do, and I find over the years that it builds a very concrete understanding of physics. Yeah, and we are all used to physics being all about equations and going to the lab after doing your equations and verifying those equations or doing some experiments, etc. But computers are all pervasive these days. And so in addition to doing physics with computers, we can also use computers to learn physics. And if you don't, then you miss out a little bit, I would say. So even if you are not convinced, hopefully by the end of today's session, you will be convinced about this. So these are the results of your questionnaire responses. So you can take a look at them to see what is the spread of different kinds of people over here. There are 37% who have not coded before. Some people have used a block-based tool like Scratch or Blockly. Some people have, about 50%, which is good, have tried some text-based programming. And there are a handful who have used code to solve problems and do data analysis in the lab, like fitting, etc. And there are even some who have used coding to explore physics ideas in simulations. Okay, so this is the spread, right? So clearly it's not homogeneous. Not everybody is used to programming. And this is good for me because it's nice to have a classroom where you're teaching something new to the students. How comfortable do you feel with experimenting with new digital tools? So this is again the spread. Everyone is quite a few are very comfortable or somewhat comfortable, which is great. 30% are sort of neutral, and there is a small minority which is a little hesitant. Okay. But hopefully this workshop will change that hesitation. Okay. Have you ever used code in a program or a program in a physics-related setting? So 63% have said no. I have not used code for a physics-related setting. You haven't used it for doing any physics, you have used it separately, maybe in your computer science class or perhaps in maths, but not to understand physics. Okay, this is again, so I asked, what's your familiarity with microcontrollers like Arduino or C-Lab? And several people have never heard of them. Several people have heard of them but don't know what they are. And a bunch of people have seen it being used on a YouTube video. Yeah, so I would imagine that the familiarity with Arduino or C-Lab or microcontrollers in general is very little. And I also asked a question, what comes to mind when you hear of computing in physics? And here are some of the representative answers that I got. Okay, it was all, you might see your response here, but the whole questionnaire was anonymous, so I don't know who's who. But anyway, so these are the responses. Using programming or simulations to analyze, model, or solve physics problems, data analysis, quantum computing, machine learning, Jupyter, writing programming codes to simplify and get visual representation of what's being taught in theory, while not being physically present in the lab, but in spirit you're present in the lab. I guess what this means is that you can use codes as an alternative to a lab, but that's not entirely true. But yeah, I mean, there is a value to that. And finally, creating simulations of physical phenomena or physics-related stuff using coding skills. So these are the representative quotations, and several of you said, what comes to mind? Quantum computing comes to mind. Sorry to disappoint, today you will not be doing any quantum computing. It will be very, very classical, old school, okay? Yeah, you look at plotting, visualization, you use Python to visualize data, or whatever you get in the lab, you use Python or any sort of programming to basically make plots and analyze the data, etc. Okay, so this is what this cohort looks like as far as computing knowledge goes. Okay. So this is these are my goals for this session. This session includes the first 2 morning sessions as well as tomorrow. So no programming experience, no prior programming experience is required for this, okay? But it will be a very hands-on session. So be prepared to do what a computer does, okay? But you'll have to do it manually, even if you know Python, all right? So it's going to be kind of a offline computing session, if you can imagine what that is. So part 1 is to motivate you to learn programming if you already don't know, if you don't already know. That's wrong English. I want to convince you that by the end of this workshop, within 2 weeks, you can learn programming. You can learn the basics of programming and you can be a functioning programmer. And you can use it to learn physics. It's not that hard. Okay, there's a huge mental block against it. But hopefully today's exercises will help you go past that activation barrier. And I want to illustrate and show how computational thinking can help you understand physics by enhancing, it can help you enhance your understanding of physics. Okay, so hopefully by the end of today, you will be slightly convinced of that idea. Part 2 is to also get familiar with the basic elements of programming. And we are going to use something that actually children use in school. So, but don't be insulted. It's just as complicated. It can be as complicated as you want it to be. It's just a very uniform platform on which all of us can do some amount of programming and get to know what you need to know in order to further your programming journey. Okay, and yeah, one of the slightly hatke bits here is to see how to interface your computer with sensors. Basically, use your computer to do experiments, to tell some device what to do. All right, so I brought with me this C-Lab kit. So this is, you might have heard of Arduino, but this is the Python equivalent of Arduino. Okay, this is called a microcontroller. Essentially, you can give instructions on your machine and tell an external device what to do with this. So I don't know how many of you know this, but at one time, computers actually referred to human beings. Computers were human beings. Did you know this? How many of you knew this? Okay, a handful of you actually knew this. And so basically, the human beings were employed to do long arithmetic calculations, like calculate logarithms, for example, and put them in a Clark's table. Okay, and these people on the left-hand side, Cecilia Payne, Pochkin, and Wilhelmina Fleming, all of these women were hired by Harvard to do astronomical calculations. Okay, Rajaram might talk about this more on his Monday session. Obviously, because of the times, they were not hired to do much more than do arithmetic calculations, but obviously capable of a whole lot more. And given the time and space, some of them went on to do much more than what they were hired to do. Okay, this is Katherine Johnson, one of NASA's Hidden Figures. Have you seen the movie Hidden Figures? Yeah? No? How many of you have heard of the movie Hidden Figures? Okay, some handful. This is an amazing movie. I have watched it about 20, I don't know. Every time I'm alone at home and I want to cry or something, I watch Hidden Figures. Okay, this is an amazing movie which shows you, it's about three African-American women who are working in NASA, okay? And basically it shows you also how the transition happened from human computers to electronic, not electronic, but machines, okay? So, and this is the Manhattan Project, and all these people sitting at those circuit boards are all computers. They were the computers. Okay, so this is what computer meant at one time. Computer was a job description. It was not a machine, right? So this is just some little bit of history I wanted to show you. And also, women have been part of this whole computing journey from the beginning. Maybe you have heard of Ada Lovelace. She's one of the first programmers. She figured out how to use Babbage's difference engine to calculate something called Bernoulli numbers. She didn't actually use the machine, but she figured out that it could be done. Okay, then later on, Grace Booth. I mean, there were so many contributors to this field. Grace Booth went on to make the first compiler, etc. So there are several women who are in this field. Clearly, it's a slightly more inclusive field than several others. I don't know what reason it could be, but perhaps because of the precedence of having so many women in that field already. Okay, so this was all happening in this Manhattan Project, etc. All was happening around the 1940s, right? And so around that same time, people were, asking what more can we do? Can we actually make a machine which can basically do what humans do? Alan Turing was one of the people who thought, look, if a human being can compute this and this and this, in principle, I should have a machine also which would be able to do the same thing. So he sort of put down some laws of computation, okay, which are used to date to design these machines, all right? And across the pond, there's this other person called John von Neumann. Have you heard of this person? Have you heard of Alan Turing? Yeah, Imitation Game, right? Better known as Benedict Cumberbatch. So on the other side, there was this other person, John von Neumann, and often there's a discussion on who built the first functioning computer. So people credit both of these guys. So I'll tell you about what John von Neumann and this other person called Stanislaw Ulam wanted to do. And then we'll just jump right in and we are going to do some hands-on activities. Okay, so we are going to use random numbers, and broadly that is called Monte Carlo method. Monte Carlo is this place where there's a lot of gambling that takes place, right? So people are always calculating odds, and presumably a deck of cards which is well shuffled, you pick the top card, it's completely random. Okay, there's no determinism. There's no way you can predict what the next card is going to be. Okay, so gambling is one of those places where you can use random numbers legitimately. All right, so these are Stanislaw Ulam's thoughts. So you can just have a look at this. The first thoughts and attempts I made, just take a minute and read this. Maybe I go back and come back just quickly. So he was sick and convalescing and was playing solitaire. And it occurred to him to ask the question, what is the probability that if I lay out some solitaire cards, I get the solution the first time I do it? Okay, so he tried and tried and tried while sitting in his hospital bed, but then sort of decided that it's pointless trying to do this in an abstract, mathematical, analytical way, and decided that he should actually go and do it 100 times and figure out the probability, right? Not a priori probability, but rather the empirical probability. Okay. So he and this other person, John von Neumann, who you can see just over here, I told you he's a big name. in this field. Both of them figured out some calculations to do. They were working on radioactive decay and I think diffusion of radioactive particles, something. And basically they came up with what is now called the Monte Carlo method. Have you heard of the Monte Carlo method? No, great. So the Monte Carlo method essentially relies on using random numbers, okay? So let me give you an illustration of the Monte Carlo method. So here what we have is a square, and within that square is inscribed a circle. So what we do is that we randomly place points on this square. We just keep, imagine that to do something truly randomly, as PK was saying yesterday, is really difficult. But suppose you have some mechanism to do something truly randomly, you manage to do it and you put points all over the square. And essentially, you can use this method to calculate the value of pi. You can see this number over here. It keeps getting closer and closer to the value of pi as the number of dots increases. Okay, so what you're doing is calculating the probability that one of these dots falls into the circle. Okay, and using that you calculate the value of pi. That ratio, yeah, that ratio is actually 1/4 of this, but
yeah, 1/4 of this.
Yeah, but you can easily do this. In fact, one of the classes that I teach, I don't even go to a computer. I just ask the students to do it physically, right? And within 10 or 20 iterations, you get 3.1. You get something close to pi. All right. So this was basically Ulam's and John von Neumann's idea. Look, I have something complicated I want to calculate. Can I just use random numbers? Can you use this, for example, to calculate an integral? Right? So basically you take a square and you plot your function in that square, and again you scatter dots. And Ulam pasta model? I don't know. Maybe. Anyway, so what you can do to use Monte Carlo to calculate an integral, for example, is to just, you have your function, and again you just scatter dots all over, and you want to essentially find the area under the curve, right? So you find the probability that the dot lies under the curve, and that is a measure that arithmetically related to basically the area under the curve. Okay, so this is the first activity you're going to do, all right? I told you that it's going to be a hands-on session. This is what you will do. I'm going to give you all a bunch of transparencies, all right? And a bunch of marker pens. So what you're going to do is simulate a random walk, but manually. Okay, so have you heard of random walks? No. All right. Thanks. Just pass on one per group. Okay, so it's good that you don't know what random walks are. Random walks are sort of one of the model systems in physics which a lot of calculations can be easily done using random walks. They are used to model processes like diffusion and also materials like polymers. Okay, so essentially a random walk is the process which I'm just going to describe. So imagine that you have a line, a 1D system line, and you have a drunkard who's trying to find his way home, okay, on this line. So right now this person is here, standing here, and what he does is he just takes random steps left and right. There's really no direction. Can't remember anything, completely blotto, all right? So, so with the probability half, this person goes to the right, and with the probability half, this person goes to the left. So once he goes here, from here also he can take a step to the right or to the left, again with the probability half, okay? And at the end, what you see if you plot position versus time, you see some sort of a, you know, maybe he goes to the right, then he goes to the left, then he goes to the left again, then to the right, then to the right, then to the right. You see some sort of graph like this if you plot position versus time. Do you agree with this? Yeah? Yes, no? Okay, so this is what a random walk is. And what you're going to do is do it in 2 dimensions. Okay, so I have passed on, the volunteers are giving you a transparency with a grid and the origin is marked, all right? So I want each of you in the group, 6 people per group, I want each of you to do this individually, okay? Do it individually and put all your results on that one transparency, okay? So I'm going to give you also some markers. Sorry, volunteers, you have to do a little bit more up and down. Just pass on some markers. Not the black ones, some colored ones. Did every group get one transparency? Yeah, you didn't get. Every group got one? Is there anyone who has not? No, okay. So let's start then. So let's go through the steps carefully and then I'll come around and see what you guys are doing. So first you're going to start at 0, 0. There is a central point which is marked and you're going to start there. At each step, you're going to generate a random number. So I don't know if you know how to generate a random number using Google. Just type in Google random number generator, okay? And ask it to generate a random number between 1 and 4. So let me show you. Please pay attention, okay? Okay, so let me show you how to do this. Just type random number generator. Okay, and it gives you this min and max, these 2 options. You can set the max option to 4. And you see that whenever I click, I get a different number. So I click, I got 1, I got 1, I again got 1, I kept getting 1. Suddenly I got 2, then 4, then 3, then 2, then 2, then 2, then 4. Right? So you see that it generates a pattern, and that pattern we'll assume it to be random. Okay? We'll assume that Google has done a great job at making this random number generator. So if you get 1, then what you have, let's go back to this, sorry. This is why I told you earlier that it's going to be a bit up and down. Yeah, so if you get 1, go to the right, okay? So let's say I got 1, I started from here and I went here, and I got 1, so I went to the right. If you get 4, then go down. So I'm here, I got 4, and then I went down. Okay, so keep doing this, and these are the other 2 options. 2, you go to the left, and 3, you go up. So I want you to plot the trajectory with maybe a black marker pen. And after 30 points, 30 steps, just draw your position with some color, blue, okay, on the transparency. All right, so there should be 6 dots on each transparency, right? Is this clear? If you have any doubts, I'll come around and you can tell me. So while we're waiting for the transparencies to come in, do you have any comments or questions? What was your experience in picking these random numbers? Did it seem random to you? No, okay. Why not? Say again? The number was varying. That's what it's supposed to be, right? That's what a random number. It's like you toss a 4-sided die. It should keep varying every time you toss it, isn't it? Yeah? You're tracing the same path quite often. Yeah. So is that, that's a good observation. Do you think it's a coincidence or do you think there's some science behind it? Okay, all right. Any others? Any other observations? Okay, one might ask, where do these people were doing this kind of problem back in the 40s? Where did they didn't have Google to generate random numbers. So what were they doing? Do you have any idea? Yeah, so they were some people actually used physical objects like dice or coins, right? But the problem with using these things is that they could be ever so slightly biased and you will never know. Okay. For example, there is some example of a bunch of, I don't know, there was this couple, I don't remember the names unfortunately, I read it in some article somewhere. They were tossing this die, they tossed it in one day around 10,000 times and looked at the sequence of numbers and realized that there were slightly larger proportion of sixes than should be the case. There should be only 1/6 of sixes, right? So there are some conditions for a process for a random number generator to give you truly random values. And it's very hard even for a computer to generate such values. So this person, von Neumann, actually had this really weird method to get pseudo-random numbers. Pseudo-random numbers are numbers which are deterministically actually found, but they have several properties that random numbers also have. So to a layman, it would be indistinguishable from a random number. And that's what computers or Google would use. Okay, so his method was to take any 4-digit number and square it and find the middle 4 digits of that squared number. And the claim was that those are actually that gives a pseudo-random number sequence. Okay, so I don't know, you can verify. Another way to get random numbers is to look at the digits beyond the 3, you have pi and you have several numbers after the decimal point. There is no apparent pattern in those points. So if you wanted to pick a number between 1 and 9, or 1 and, if you get 0, then you could call it like 10. Then it's not a bad idea to just keep going through all the digits of pi. Anyway, there are several now very sophisticated algorithms. People keep spending a lot of time on worrying about whether a random number is, gives better random-like qualities. Okay, so are the transparencies ready? Mostly done. Oh, it's all. Okay, so now I would like to just take all your results and see what the result of your results. So this is where we started. You can imagine that this origin is actually is a little drop of ink, and okay, so I'm going to keep overlaying these points. Okay, you all should have made little larger points, but anyway, let's see how it looks. Yeah, I can't see any of these points. Who can see this? Can you see them which are projected? They're really tiny, conservatively plotted. You should just, make a huge point like that. That is better. Okay, so someone has plotted the path as well. Are you able to see? Very lightly colored. I can't tell anything actually. It's kind of difficult. Huh? They're all in different orientations.
Orientations are different. But is it not square? It's square, right? Oh,
so, yeah, it's just the origin is at different points.
Oh, each one is origin at different points. Okay. No, but if you do it like that, it will not just like.
Yeah. You can just put the square on the square.
No, it's not towards.
Because the printout is.
Oh, printout.
Let me do it. Let me do it.
No.
Okay.
Little. Yeah. Sorry, I missed it. Yeah. Some of them are gone, no?
It's okay. Okay, so yeah, well, the results are as good as the experiment, okay? So can you tell me your observations from this experiment? What do you see? If you can see anything at all, what is it that you observe? Yeah, so you would imagine you have 30 steps, maybe some of them would go all the way to the boundary. Very few of them actually reach the boundary. Yeah, we'll wait for PK to finish what he's doing. And okay. Yeah, all right. Yeah, this is fine. I mean, it's fine. Okay, so and what else do you notice? Does it look like some physical process to you? What do you think is? I told you that random walks are often used as a model for diffusion. Do you think that somehow this could be related to diffusion? Yeah. Okay. All right. Yeah. So what you can see is that some particles go to some distance. They travel a little farther than other particles. There are other particles which may have traveled that much, but would have maybe come back to the place where they started. So there is a spread. The molecules have, I mean, the points have spread. Okay. So yeah, so this is often used as a model of diffusion. Can you suggest maybe some sort of quantitative measurements one can do with this kind of data? What would you measure? Is there something that you would measure? Distance from origin, okay. Yeah. So how far has it, distance from origin as a function of time, right? So that's a good measure. Anything else you would like to measure with this? Huh? Sorry, I can't hear you. Shortest distance. What is that? Yeah. Probability of finding a particle at a particular point. Yeah, that's a great idea. Anything else? Shortest distance. Maybe we have to rework that a little bit for slightly different procedure. Anything else? Yeah? Okay. All right. Yeah. So there are all these measurements you can do, right? And essentially what you have done is not a theory. It's not like pen and paper theory, the way we think about it. And it's not an experiment also in the true sense of the word. Okay? It's a simulation. It's something that we say, okay, maybe I feel like doing this. I have a point, I'm just going to keep tossing coins and see what happens. All right? And at the end of it, you get something interesting. First of all, you see that the point spreads, and you can ask, how much time does it take to spread? What is the average distance of a point from the origin as a function of time? All of these questions can be asked. Okay, so I'm going to leave that as homework for you to do. I'm going to move on to the next activity now. Yeah, please. And if I run this, if I do 60 more steps, what do you think would happen? What do you think would happen to the probability of being near the center? Increase. Okay. Some people say there are three possible answers: is increase, decrease, say stay the same. How many people say increase? Okay.
You understand the question? 60 steps now instead of 30 steps. But yeah, you said it will increase. Yeah.
Okay. What about decrease? How many say decrease? Small number say decrease. Okay. And how many say it stays the same? It doesn't matter how many. Okay. This is another thing. I won't tell you the answer. You will have to check this. Okay. So I've got a PDF which I'll give you for homework, and I would like you to do this and check these things quantitatively. Okay. So at night, when the lab is, somebody said, right, while not physically being present in the lab, you can do some physics. Right? So this is what you're going to do. Keep tossing coins. All right. I'll move on to the next activity. So the next one is also about diffusion. All right. Um, so, so I'll ask you a question. I have a compartment. Okay. I have some sort of container, and I have a partition in this container, and I put some ink particles on the left-hand side of the container. They're all only on the left side. Okay. Now I remove the partition. You can remove it, and I'll connect my computer. So what do you think would happen once I remove the partition? Huh? You've all done this a number of times. You can say with great confidence. What do you think would happen? It will move to the other side. So these ink particles are going to move somehow to the other side. So, typically when things move, we say they are experiencing a force. I mean, when they are going from static to moving, then they have experienced some force. So do you think these particles are experiencing a force? Is there a force? What do you think? Is there a force experienced by these particles which is making them go to the right side? Are they being pushed from the left to the right side? Yes? Okay, where is that force coming from? The interactions between the particles is giving you some force, okay, that's one. Okay. Any other answers? From the left wall of the container. Reaction force is pushing it all the way to the left, all the way to the right. It's still there. Okay. So are these forces directional? These forces that you're talking about? Interactions, collision with the wall. Do they have some direction? So is there any pressure here? Is there any difference in pressure? I have water on both sides and I put a little bit ink. Do you think there's a difference in pressure on both sides? Mm-hmm. Yeah, right. So it seems to be some sort of inevitable consequence, while it doesn't fit into our Newton's formulation of mechanics. Newton's force move. Okay, so there is something which is making it go to the other side, right? And it seems like it's just a inevitability. Okay. So the next activity is going to get you to think about this process. Again, I'm not going to give you the answers. At the end of this, hopefully you will have more questions which you can ponder over. Okay, so let's all right, so this is the second activity, okay? And this is what I want each one of you to do is to take your notebook and first make a partition in one page. Just draw a line to partition the page into two halves, just like this system over here, okay? And then I want you to tear up a piece of paper into 10 little slips and number them. So I want you to number them 1 to 10, okay, and place them all face up on the left side. It can be right, but do it on the left side. Okay, so I'll move on to the next set of instructions. Did everyone understand this? You have to partition your page and then just write 1 to 10 on small chits of paper and place them all on the left side. Okay, so then now what we're going to do is start moving particles. Okay, so what you do is go to your random number generator and generate a number from 1 to 10, including 1 and 10. Once you've generated that, you find that slip and you move it to the other side. Whichever side it is on, you move it to the other side, okay? And you can, what you are going to record is the number of slips which are left over on the left-hand side. So if I pick, for example, 10, then I take 10 and move it to the right. And in my notebook, I write down time step 1, 9 are left on the left side, okay? This is again a manual simulation. And I want you to do this for 50 steps. Each of you is going to do this for 50 steps. So do it independently. Note down your result. And once everybody has the results, enter it on an Excel sheet, okay, and average your results and plot it.
So at 10th step, if the 4 is on the right side and you get 4, then you go to the left. Yeah, so to the other side. Not only right to left, it can be left to right.
Yeah. Did you understand what I said? Anyone with any doubts, please ask. Huh? Repeat, okay, okay. So what I'm going to do is basically, I keep leaving it somewhere, sorry. Yeah, so suppose your random number generator gives 3. Then you take 3 and put it here. Okay, suppose it gives 5. Then you take 5 and put it here.
Suppose the next one also gives 5.
Suppose next one also gives 5, then you take 5 and put it back here. Vapas rakhna hai. Okay.
Every time you get a number, take that seed and put it to the other side. Wherever it is, take it from there and put it in the other box. There are 2 boxes, right? Take a random number, take a seed and put it in the other box.
Yeah.
And you are counting only the number of seeds in the first box, left box.
In every step, you find out how many are remaining in the left box. How many are there in the left box. Record that. So this is your manual computational experiment, okay? You understood? You have a question? Record the number left in the left compartment. Like at the end of the... No, in every step. Yeah, you'll have 50 points. Yeah. Did you understand? Yeah. What's your question? Yeah. Yeah.
Each time you have to record the value.
Yeah. Each time you have to find the number of chits on the left side. Just count like 1, 2, 3, 4, 5, 6, 7 and write down 7. Maximum will be 10. Yeah.
Like I do this, record 2. So I will use this 2
Put
left
it,
side.
put it on the left side.
And this I have to do 50 times.
Yeah.
Left
No, at each step you need to find, record what is left.
So, like means then first step that I need to know how much left sides are there.
Yeah.
Okay.
In every step you need to record that. Yeah. You should contribute. This all works only if you're in a group. Okay. Okay. Yeah. Once you've finished your recordings, you can add to the groups because you have to club your data and plot the average. Yeah. Once you're done with that.
We have to do it for every step, right? Like I do one movement and then I check.
Yeah.
That.
Yeah. Yeah.
After all that, we'll take the average of number of chips for each step and then
Yeah, you can plot your individual data and see what it looks like. Then one of you can take responsibility, gather the data from everyone, and find the average and plot it and see what that looks like. You could just directly put in your data on an Excel sheet. That would save time. Okay, so this is what your Excel sheet should look like, okay? So first I have time, then student 1, student 2, all right? And you have student 3, student 4, student 5, student 6 for all, right? So maybe in time step 1, one of the things has gone, so you'll have 9 here. Pretty much everyone will have 9. Okay, and each person records their data, and finally you take the average of these 6 columns and put it in the final column. And I want you to plot both of this. Your individual data, you should plot it and look at it. Okay, and you should also look at the average data once it's done. Is this clear? Yeah. Who is calling? Who called? Okay, so we have some results coming out, just maybe a couple of minutes before tea, so you have something to think about. Can I have some broad observations? How does the number change? Like this. Huh? Again it went up. Okay. She says it's increasing and then decreasing. Okay. Any other observations? Quickly, any observations? No? You haven't plotted yet? Okay, so rough, do the numbers, so what happens after some time? Initially, what's happening? Initially, what happens to the number? Decreases. It decreases, right? After some time, what happens? It's kind of like this, but it keeps going up and down, right? So yeah, so initially there's a drop, and then it reaches some sort of a equilibrium state, and there are some fluctuations about that. Okay, so yeah, we're not doing very well on time, but that's just my miscalculation. It doesn't matter at all. We don't have to complete all the activities. We'll discuss a little bit more after you come back from tea.